All right, welcome back. Now let's look at the dynamic characteristics of the instruments. So till now we had seen some of the features of the instrument that was more static in nature, where we said some of the 11 features that we saw for an instrument, which are to be specified for an instrument. Some of the instruments may have all of those features, and some of them may have one or the other. But there are instruments actually where dynamic characteristics is also very important, because there are some instruments which take time, or which take time actually in responding, which have inherent inertia in them, and which have actually some of the other physical components that actually make them of different orders, and obviously they have their own features actually which needs to be taken care of. Now we define the dynamic characteristics of the instruments. It is the actually the it describes the behavior between the time a measured quantity changes value and the time when the instrument actually attains a steady state in response. So in a very simple sense, if we still assume that there is a step input, or there is a change in the quantity. For example, we want to measure the temperature of some liquid, and obviously we assume that this temperature is not changing. Let's say it reached a steady state where the temperature is constant, and we want to measure this temperature. Now there are there are instruments actually which could be used. For example, a thermometer can be used, but thermometer in its inherent design has some features that it may take some time to actually reach to the temperature that actually the liquid is of. You must have also seen a very common example in our domestic life, where we use a thermometer to actually measure the temperature of the human body, where we put up a thermometer below the tongue, and we see after some time it actually attains the value that the temperature of the human body is. So rather than directly giving us the output, it takes some time actually to reach to that point. So that is actually the dynamic characteristic. We can say that it's the behavior between the time a measured quantity changes value and the time when the instrument output attains a steady state value in response. So now let's assume we have a simple case where the input really doesn't change much, but the instrument actually has a design in which, because of which actually it takes some time actually to reach to that value, to the output value. So this will be more clear with the other examples. Now in this case, the performance characteristics obviously are become something called a speed of response. How rapidly the instrument responds to the change in the measured quantity. For example, now the temperature changes. How much time does it take for the instrument actually to come up with the final value of the new temperature? So that's very important, that we call as speed of response. Something called as dynamic error, the difference between the true and the measured value with no static error. Lag, the delay in the response of an instrument to change in the measured variable, which is similar to this, or analogous to speed of response. And fidelity. Fidelity is actually the degree to which an instrument indicates the change in the measured variable without dynamic error. So this is more a faithful reproduction of the actual value that we want to measure actually. So these four actually characteristics are there with the instrument. So the most important is actually the speed of response, or the lag with the instruments, and also the errors that the instrument actually can minimize, and all those things. Now we go for this type of dynamic characteristics. So it is obviously time dependent. So we have something called differential equations that come into this in the design of instruments. So we can design for in a linear time invariant measuring system. This type of relation can be written between the input and output. So for example, Qi is the input and Q naught is the output. So we have between the input and output, this is the relation, is equal to sign. So you have a linear time invariant differential equation, which talks about actually output here, the rate of change of output, the higher order differential of the output, and obviously the input, and then the rate of change of the input, and accordingly higher differentials of the input. So obviously this is a very generic expression, or a very general expression, or a relation between the input and the output for a time invariant linear measuring system. So obviously a relation between the output and the input. So this is more of about inputs, where the input could be any measurand, and the output could be obviously related to the actual instrument that we have designed. Now, according to the order of the differential equation, actually we define some, we give terminology to the instruments also. For example, we have something called a zero order instruments. So zero order instruments obviously will be, well, the differential part is obviously zero. So now if you look back to this, so we have just this part and this part remaining on the left and right hand side. So it becomes something like this: A naught Q naught is equal to B naught Qi. So which means that we call this as zero order differential equation, sorry, a zero order system in this case, or a zero order instrument also, where there is no dependence on the rate of change of the input, and there is nothing called as rate of change of the output. So obviously whatever we are giving input, it bears a linear relation with the output. So there are some instruments where we can see in the examples there that the input or the output bears a linear relationship with the input, and it's very static. So this is more static, or you can say more simpler in its expression. But in the first order instruments, obviously this is what it could look like. So you have the first order differential, and similarly for the second order you have this way. So generally we deal up to second order differentials only as a practical examples. For higher order we can do simulations and all, which we do not deal in this let's say course. Now in the zero order instruments, this is how the input and output will respond. The output will respond to an input. So this is the measured quantity. For example, you had some value qi, and now, sorry, at this instant you had qi. Now it becomes qi dash or something like that. So which means there is change in the, or step change in the input, and accordingly you have a similar step change in the output. All right. So this change could be obviously different based on the linear relationship between the input and the output. So this is how we can write it, rather than saying a naught q naught is equal to b naught qi. So we can write it this way, where k, capital K, is obviously b naught by a naught as per the definition of the zero order instruments. So this is also known as the instrument sensitivity. Now this is what we have already discussed in the static characteristics also. So the instrument sensitivity is nothing but the slope of the input and the output. So this is very simple. So in this case we can say zero order instruments, and the instrument sensitivity is actually more of a static characteristics rather than a dynamic characteristic, because dynamics actually comes into play when we talk about actually first order and second order instruments. Now obviously if we look at the example of a rheostat, where we actually try to measure the position of some, let's say position of some object, and we want to measure the motion, and we can just connect it to a rheostat, and the way it actually moves, the resistance changes, and we have the change in the output voltage, something like this. So E naught is proportional to the distance xi. So this is very much linear, and this is very much simple and straightforward. So these are actually the zero order instruments, where there is no lag, where the speed of response, there is nothing called a speed of response. The moment you give input and you have the output at the same time. So if the input actually varies something like this in terms of the distance, the output is exactly mimicked in the same way in terms of voltage. So obviously we have something called as frequency response. We don't deal with those things in the zero order instrument. That we'll see in the second order, first order and second order instruments, these types of quantities like frequency response and other things. So in this case we don't have any phase change and all those things. We'll see it later on. Now the example could be of a potentiometer that we have just now seen. You move this pointer over this rheostat, or you can use this slider to actually measure the position. So the moment it goes front and back, accordingly it changes the resistance, and you have the output in terms of the output voltage. So this is quite straightforward. So a potentiometer can be used to measure motion. Now the zero order input instrument, or you can say zero order instrument, the output changes instantaneously as the slider is placed along the potentiometer track. Another example could be of a strain gauge, where you put these rosettes, strain gauge rosettes actually, or strain gauge, these bonded strain gauges on the specimen, and then tension can cause resistance increase, compression can cause resistance decrease, and all those things. This can be put in a quarter bridge strain gauge circuit, and the moment there is some compression or tension, then accordingly it changes the resistance. You can easily find out the equivalent bridge resistance, and accordingly you can find out or equate that to the strain on the member. So this is again a zero order instrument, because there is nothing as a cause of a lag and other things. There's a direct relationship between the input and the output. And these types of strain gauge or any other strain gauge could be actually used not just for the tension or compression. It could be also used sometimes to measure the pressure. You have some strain gauges and an elastic body in between, and you can actually, because of the high pressure, this strain gauge can actually deflect, or you can attach some strain gauge rosettes, and accordingly you can find out the pressure of the gas or any other fluid. Now coming to the first order instruments, Obviously, the mathematical expression in this case would be something like this, which we have already seen as from the generalized one. Now, mind you that we are actually discussing very simpler cases in which we assume that there is only a step change in the input. So there could be cases where the input obviously also changes dynamically, which makes it more complicated. That is not actually the part of this course. That can be seen in higher degree courses that we can look at there. But in this case, we're just concerned with actually the assuming that the input is actually constant, or you can say static, and then the instrument design is such a way that it is a dynamic, it has dynamic relations with the input. So then in the first order instrument, obviously you can see this is something that we have already seen in controls also. So you have the measured quantity, that you have a step input, and the measured quantity, this one, and this is the instrument output actually. So this is how the instrument actually responds because of this type of expression. And obviously we have something called as time constant in these things. We define time constant, we define the rise time, we define the settling time. All those things are actually that we have seen already in controls also. So we can make this simpler. The capital D represents the d by dt part. So in this case we define the static sensitivity as b naught by a naught. So we can maybe simplify this differential equation in this form. So K is defined as the static sensitivity of the first order instrument, and tau, which is A1 by A naught, the coefficients associated with the out instrument, define the time constant of the system. So mind you, this is very important. This left side actually talks about the instrument only. This is about the measurand. Now this is the property of the instrument. So instrument actually here is of first order in nature, which means instrument actually will not respond so quickly. The moment you change the input, it will not actually change the output. For example, in this case, you have seen the input was made as a step, or can say measured quantity. We dipped a thermometer in a glass, in a hot water tap, but after some time only, actually, the thermometer showed us the thermometer predicted the actual, or you can say the thermometer display the correct value only after some time had elapsed. Now this is something that happens with the instruments. So obviously there could be other ways of measuring this. So these days we have infrared based thermal imaging, or we can say infrared based temperature measuring devices. They could be even better than this, but maybe these are cheaper and those are expensive. So all those things are there. As technology evolves, you use different techniques to do these type of measurements also. But let's say, for example, if we have this instrument that we have with us, let's say, for example, a mercury bulb thermometer. So this is how it will actually respond. This obviously happens because there is mercury, which absorbs some heat first and then actually expands. So that natural process of actually, taking up the heat, reaching to a state where it actually starts expanding. So that thing is actually associated with any physical process. So that's where we design actually instrument. We take care of such things. But obviously, we want to make a faster system, so we have to see how we can actually, reduce this A1 by A naught ratio. So these things can be, we can use them actually in the design of new instruments. Accordingly, we see what actually these parameters refer to in case of a thermometer or any other instrument. We will see one example of a liquid in glass thermometer, where we will see what actually A1 and A naught refers to. These are not just the constant, but they have some specific meaning, or they have some specific significance to the instrument itself. So this is the typical thermometer that we see. There is mercury here. As we dip it in the hot water or any other surface, so it expands and then it takes in the form of a capillary, goes up as per the temperature. Actually, it actually points to that value. All right. So now this mercury bulb thermometer is a first order instrument where there is some delay, where there is some actually energy absorption taking place. This is not similar to the rheostat, where actually we move the slider and then we have the output, but rather we have some energy conversion taking place, heat being taken here, and then it enables, or it leads to the expansion of the mercury. So it takes some time actually to do such things. So obviously there is some delay. Now we can always model this as an example of a mercury bulb thermometer. There are physical processes. Actually, it's nothing but a heat transfer that is happening from the liquid, or you can say from the measurand to the mercury bulb. There's heat transfer. It depends on the surface area. It depends on the mercury. It depends on the density of the mercury. and all those things. So with all those things, if we want to model such thermometer or any other instrument for that matter, so we'll have to use obviously those the physics behind all these processes, and we come up with some equations in this form, where we have the temperature as the input and x naught, which is the height, or you can say the gradients on this, the scale on this actually tells us the output. So this is the relation that it follows, where it's nothing but a first order system equation. So now let's say this is the tub, glass tub, which has some temperature Ti, capital Ti, which is to be measured, and obviously you have some mercury bulb where you have some T, capital Te. So these are the equations that we generally use. So again, a first order differential equation has been used, and then it can be modified in this form, and then we can actually write it in this form finally, where k and a tau have a meaning. So k and tau has a meaning here, which is actually similar to what we had used as k by tau d plus 1 in this case, where k is given by this and tau is given by this. So all this equation actually is nothing but a first order differential equation. So this was our kind of a1 and this was our a naught. So obviously now they are not the constants, but they are having specific meaning, where rho is nothing but density. It could be density of the mercury. C is the specific heat. Similarly, the area of the bulb, AB. So all those things are actually together, and then this actually gives you the governing relation between the input and the output. So Ti is the nothing but the input, which is the measurand, and this is obviously, as I have told you, this is related to the measurand, and this is related to the instrument itself. All right, so these are the properties of the instrument, where rho is the property of the instrument, which is the mercury density. So this is the obviously the step response. This is the step input. We have dipped the instrument in the liquid, and this is how the mercury based thermometer will respond. For a smaller t, smaller time constant, it will respond quickly and reach to the steady state value, but for a larger t, it will reach after a quite longer time, which means if we go back for a larger t, means having a smaller AB, it may take more time, or if we have a smaller rho, so it may take lesser time, because tau is proportional to rho. So accordingly, we can design thermometers with different tau, with different sensitivity and all those things. This is just to add, this is the ramp response. If we give a ramp input, obviously, which means that the input is also changing. So this is the rate of change of input, which is nothing but a constant slope, and this is how actually the output will actually respond to this. And then we have something called as frequency response, where we basically use the same relation, and instead of the differential, we use I omega to try to find out what happens actually with the the frequency response of first order system, where we basically see the response of these instruments to the changing inputs also. So we come up with something like this as an expression that we have already you must have seen in control systems also. This is how we find out the amplitude ratio, and this is the phase angle, and this is obviously dependent on the frequency. So this is how it looks like. So we have the output upon input. This is how it looks like at higher frequency and into time constant. A large change, you can say it is really undesirable, and with higher omega tau also, again you have a large phase shift between the input and the output. So here we say something called attenuation that happens. So we have a very small output for a good amount of input. We have very small output because there is a lot of attenuation that is happening. So we'd always like to have this omega tau to be near to 1, which is always desired, so that we have the least attenuation and then the least phase change between the input and the output. Another example could be of a thermocouple, which is again a first order instrument. It also takes some time actually to respond to the input. Thank you.